Welcome back to the Deep Dive. Today, we're looking at some research that really challenges how we think about LLM efficiency, specifically after the training is already done.
Right, we're talking about test time scaling, or TTS.
And if you've ever worried about API costs or latency, this deep dive is for you. TTS is, at its core, just the strategy of improving model performance by giving it more computational resources during inference.
It sounds simple, doesn't it? Just, throw more power at it. But the problem is that the traditional ways of doing this are incredibly rigid.
How so?
While they assume a one-size-fits-all architecture, you might say stack models one after another to refine an answer or run them all at once in parallel.
But that structure is fixed from the start.
Exactly. And on top of that, they usually just rely on a single big model. This whole approach, it leads to a ton of computational waste because the best way to solve a chemistry problem is, completely different from how you'd answer a history question.
And that inefficiency is exactly what this research is trying to fix. They've moved past this static idea and are asking a really novel question.
Which is, how do we find the compute-optimal combination of models and architectures, all while staying under a fixed budget?
They've formalized this as a search through what they call a multi-LLM collaboration graph.
And we have to be clear about the difficulty here right away. The search space for this is, well, it's almost unimaginably large.
Give us a sense of the scale.
Okay, so if you're working with a graph of just 12 nodes, so 12 model operations, the number of possible ways you can connect them is somewhere between 10 to the 18th and 10 to the 26th.
That is a truly astronomical number.
It is. I mean, to put it in perspective, if checking just one of those graphs took 1 second, exploring 10 to the 18th would take longer than the age of the universe.
The brute force searching is completely off the table.
Completely impossible, because every single one of those candidates requires a full, costly inference run to even see how well it works. The whole solution has to be about designing a smarter, more efficient way to search.
And to justify that effort, the research first had to show exactly why the old fixed systems fail. They pointed to two critical limitations. Let's start with the issue of fixed topologies.
Right. Their inability to generalize is pretty striking. They found that different tasks really do need fundamentally different architectural patterns.
For instance,
Take two common setups. One is a hybrid structure. It mixes parallel work with sequential refinement. The other is a pure parallel structure where a bunch of models all tackle the problem at once.
and the results were basically polar opposites depending on the task.
That's right. For complex reasoning, like in the math dataset, that hybrid approach was the clear winner. It hit over 50% accuracy. That refinement step was clearly crucial.
But on a different task,
But when they took that exact same architecture and applied it to MMLU, which is more of a knowledge-based task, it performed poorly. For MMLU, the pure parallel structure was much better. It shows that for broad knowledge retrieval, you want consensus, not lengthy refinement.
so the idea that one scaling strategy fits all is just demonstrably false.
It is. And that brings us to the second limitation. This reliance on using just one single large model.
We tend to assume bigger is always better.
But the data here shows that's not always true. Multi-LLM ensembles using several different models can be much better because they can leverage different skills.
I think the math dataset example was really powerful here.
It was a single 8 billion parameter model got about 49% accuracy, which is, pretty good.
But the ensemble,
But when they used a targeted ensemble, a mix of 3 separate 3 billion parameter models working together, the accuracy jumped all the way to 57.7%.
so for reasoning, 3 smaller models collaborating were significantly smarter than one larger one acting alone.
Precisely. Now, for MMLU, the single large model was still better. But this just reinforces the core problem. You can't just buy the biggest model and expect it to be the best and most cost-effective solution for every single task.
Okay, so to get around these limitations, the research proposes this multi-LLM collaboration graph, which they call G.
And this graph is basically a flexible blueprint. It can dynamically determine both the topology, how the models are connected, and which specific model gets assigned to each step.
And the nodes in this graph have specific jobs, right?
Yes, each node is an LLM primitive, and it gets assigned a role. You have the assistant role, which is all about sequential refinement. It takes output from a previous step and tries to improve it,
Like a copy editor.
a very meticulous copy editor. And then you have the fuser rule. This one is for parallel scaling. It aggregates outputs from multiple different predecessors to synthesize a final answer.
And the whole goal is to find the perfect mix of these roles and models to get the best performance for a given computational budget.
Exactly.
So given that impossibly large search space, they couldn't just use a standard optimization algorithm. They needed to be smarter. They ran some pilot experiments that gave them 3 key insights, sort of the aha moments that make the whole system work.
Right. These insights are the blueprints that guide the search. The first one is about model choice, what they call task-specific preferences for model combinations.
And the takeaway here wasn't just use the best model family.
No, it's more nuanced. The critical part is about the size trade-offs. For reasoning tasks, like math, the data clearly showed a benefit from using ensembles of smaller models.
Why is that, though? Why wouldn't one big llama model be better?
It seems to come down to the nature of reasoning itself. It's often multi-step, and errors can creep in at any stage. An ensemble of smaller models allows for more iteration and checking. Each small model can refine the previous step's work more efficiently.
Whereas a knowledge task is different.
Right. A knowledge task like MMLU prefers that single larger model. In that case, more parameters really does mean broader knowledge coverage and better recall.
This sets up what I think was the most surprising finding, Insight 2. Non-monotonic scaling and budget saturation. This just flies in the face of the more compute is always better idea.
This is the part where you learn that your LLM can actually get dumber if you spend too much on scaling it.
Oh, really?
Yes, both width, which is parallel scaling, and depth, sequential scaling, follow this non-monotonic curve. Performance gets better as you add resources, but only up to a point. After that optimum, it plateaus, or, and this is the key, it actually starts to decline.
Can you give us an example of that negative return?
Sure. On the math task, they saw peak accuracy with about 8 parallel nodes or 8 sequential nodes. If you go beyond 8, you're not just wasting compute, you're actively hurting the final result.
Why does that happen?
With too much depth, the model starts amplifying errors instead of fixing them. It literally refines itself into a mistake. With too much width, you just hit diminishing returns so fast that the extra cost gives you zero benefit.
So the search has to find a ceiling, not just a floor. Which leads us to the third insight, the interdependence between graph width and depth.
Correct. Since your total budget is fixed, say, a maximum of 24 nodes width and depth are a trade-off. If you make the graph wider, you have to make it shallower.
And that changes the optimal point for the other dimension.
It changes it entirely. For math, if your width is 1, so it's purely sequential, the best depth is 8. But if you increase the width to 3, the optimal depth suddenly drops to 4.
That makes sense. The initial parallel work solves part of the problem, so you need less refinement later on.
Exactly. The search needs to manage this constantly shifting relationship.
So these 3 insights become the fuel for their search engine, which they call the agent-reinforced framework.
Right, and this is an LM agent that's built on a probabilistic algorithm. It follows a simple loop, sample feedback update.
But the key is how it uses those insights.
That's the difference. It's less like a blind mathematical search and more like a smart coach refining a playbook based on game footage.
So how does the coach start?
It uses Insight 1 to do some initial scouting. It finds the best starting model, family, and size for the task, so it's not wasting time. Then it samples a graph structure. If that structure performs poorly, the LLM agent uses that feedback to update its strategy for picking the next configuration.
And insights 2 and 3 help it avoid bad plays.
Yes, they help it steer clear of configurations that are known to waste the budget or have poor width-depth trade-offs. It makes the whole process converge much, much faster.
And the results really bear that out.
Yeah.
It performed incredibly well against more traditional methods.
Absolutely. At a budget of 80, Agent Reinforce got the highest average score, 61%, across math, MMLU, and human evil.
But the real story is the efficiency.
It really is. Because the search was guided by those insights, it was incredibly fast. It took, on average, just 532 seconds to find a good solution.
Compared to what?
Compared to random search, which took almost 1,700 seconds, or Bayesian optimization, which was way behind at over 2,600 seconds, we're talking about finding the optimal setup in a fraction of the time.
And the ablation studies proved that this speed up was because of the insights, not just luck.
That's right. If they removed Insight 1, the smart starting point, the search slowed way down, and the final accuracy on math dropped from 56% to 45%.
So the insights aren't optional.
They're the necessary condition for solving this efficiently.
So what did the final optimal graph actually look like for a tough task like math?
The graph it found for math was a perfect confirmation of everything we've discussed. It used ensembles of small models, proving their value for reasoning,
And the structure.
and its structure was a hybrid, biased toward that sequential refinement we talked about. Specifically, it had a width of 3 and a depth of 4, a beautiful balance of initial exploration and iterative refinement.
This deep dive really makes it clear then. The future of getting optimal performance from LLMs isn't about static scaling anymore.
Not at all. It's about adaptive, graph-based optimization that uses empirical knowledge to perfectly balance performance against your budget.
A major shift in thinking.
And for anyone using these models in the real world, maybe the most powerful part of this work is how they define budget. It isn't just a theoretical metric like
You've
FLOPs.
generalized it.
They did. The optimization can handle complex goals, like maximizing performance while also minimizing latency. And crucially, the search can operate using monetary cost, actual dollar cost, as the budget.
Which makes it immediately useful for anyone paying for API calls.
It makes it immediately relevant. That ability to optimize directly for dollars and performance at the same time, well, that's the ultimate takeaway here.